Have any of you prepared slides for this 2-minute presentation?
So I have some slides.
Okay. Do you want
I
to?
also have, yes.
Are you confident that your screen share is working, or would you like to try it briefly?
I would like to just check briefly. Sure. Let me just see if I can do that.
I mean, all of us have been spending too much time on Zoom, so probably some of you might already know it's working, but it's always a good idea to try it. So do we have to do anything special in terms of, no, he's able to share. Okay.
This works.
Stackelberg. Okay, that's good. I think it's time to start, according to my watch.
Sorry, Peter, just one small question.
Yes.
So the introduction is limited to 2 minutes?
Yes, I think, or was it supposed to be 2 to 3 minutes?
I don't know. Yeah, we are discussing this actually with Michael, and we are not sure how many minutes we are supposed to.
Well, let's aim for roughly 2 minutes, right?
I think maybe I can say something here. We thought if we say 2 to 3 minutes, then everyone understands 5. If we say 2 minutes, then it's not 5.
Right.
That's all.
Yeah.
Okay. I
mean, if you talk less than 2 minutes, it's good. Then there'll be more time for questions, right? It's really not a talk. It's just basically saying, this was the paper. So prompt people. Okay, so shall we start we're streaming now. Okay. So welcome to the audience on YouTube and the audience on Slack and the audience on Zoom. And welcome to this session C4 of ICALP. And we have 6 papers. Each of the groups of authors is going to give a brief presentation, and then we open the forum for questions. So the first of these papers is, which one is it? So that's by Titouan Carrette and Emmanuel Jandel, and a recipe for quantum graphical languages. So please go ahead.
So you see my screen?
Yes.
Okay. So I'm Titouan Carrette, yes. And so what we have done with Emmanuel Jandel is that we design a graphical language for quantum computing. So a graphical language, we have kind of boxes with inputs and outputs, and then we build bigger diagrams with them by plugging them or putting them side by side. So this is basically a symmetric modular category. In the context of quantum computing, we are more interested by qubits. So a diagram with n inputs and m outputs is a linear map from C to the 2 to the n to C to the 2 to the m. So there are different graphical language for quantum computing, mostly 3 of them, the ZX calculus, the H calculus, and the W calculus. They all are different, but they share kind of a common structure. And in fact, this common structure also appeared in a completely different work, not about quantum, but about control flow graphs, which is what I will call graphical linear algebra here. So what we have done in this work is to define what is the common structure of those 4 different graphical language. We called it this star algebra. So you see the graphical language here. We have some generators and you have some equations. And then we have found a clever way to decompose this graphical language in order to classify all the different language like this we can find in quantum computation, but also in the context of graphical linear algebra. And the result, so it was not so surprising for us, but in fact, for qubits, in quantum computing, we already knew all of them. Those are exactly small variation of the X, the H, and the W. And for a graphical linear algebra, again, the one they discovered was essentially the unique one. So the main point of this work is to say that we are now a clear view of the link between the different quantum graphical language. And we know that if we don't have a very different new idea of the graphical structure, then we already know everything that we can find for quantum computing using Z-star algebras. So as a further work, we can try to look at qubits. In fact, usually in classical computing, we never speak about DITs because they are simulated efficiently by bits. But in the quantum case, we're more hardware dependent. So we can have physical system with 3 states or 4 states. And this can be, so this could justify why this could be relevant. And here we don't know, this is more wide. That's all. You're still muted.
Just trying to unmute myself here. Thank you very much. I'm going to clap on behalf of everyone because everyone is muted. But so let's have some questions. Are there any live questions, first of all?
So
yes.
There is nothing happening in Slack. Of course, it's the moderator invites question now here in Zoom. You can just unmute. There has been some discussion inside Slack, which I also find somewhat intriguing. I mean, one could imagine if one takes a number of languages that are all motivated by something and then tries to find the common core may be very boring, right? And it may not be able to express what is really behind the essence of qubits. And it seems that Andrea Torini tried to discuss this a bit with you, Titouan. You want to reiterate a bit the discussion there?
Okay, so for me, there is two different questions here. So the question of Andrea in Slack, if I remember, was about specifically entanglement and no copy, which are two key features of quantum. And he asked me, how can I see them, represent them in a graphical setting? And in fact, in graphical setting, entanglement corresponds to connectedness. For example, just here you see you have a connection between those two nodes. So you know there will be some entanglements between those two groups. Okay. So this is how you see entanglements very quickly, of course. And about non-copy, the idea is that when you are doing a graphical language, you are in a symmetric monoidal category. So from the start, you don't have any way to copy or erase data. You need to add it to your language. And when you look at specific language for quantum computing, then you don't have this copy of erase map, except only on the basis, which is exactly what you have in the non-copy or non-erasing theorem for quantum computing. And the other question is, if you find the common core, is this common core interesting or not? So this is more technical, but if you look at this common core, in fact, this might seem completely ad hoc, but if you look at those equations here and here, you quickly have them if you require some topological properties of your language, that your diagrams must look like graphs. So this you can justify by those kind of topological arguments. And the only ad hoc equation that remains is really this that we call the B-algebra rule. And in fact, this is one of the most simple, non-trivial equation you can require in a graphical language. So if there is something, you can wonder if this is very meaningful for quantum computing, or if we're just not able to imagine something else. This is about this B-algebra rule here.
Okay. Thank you. I have one question. So you mentioned sort of in the further work section, I think that the classification you gave is for qubits, right?
Yes.
So for qubits and higher, it's sort of still open. How typical do you think the qubit case is? Like, you found that there's only finitely many up to isomorphism models of this, but do we expect for qubits, could there be infinitely many?
Okay, so a good way to have an idea is to look a special case of those things here, spiders. Inside this, you have just a monoid, which is just in fact a C algebra here. So your question is linked to the number of C algebras up to isomorphism. In dimension 2, we only have 2 of them. They are all commutative. Mm-hmm. But if you go in dimension, I don't remember if it's 5 or 6, but very quickly you have an infinite number of algebras up to isomorphism.
I see.
So it's possible that because we have further requirements, then we have kind of collapse and we see that we have finitely many of them, but I doubt it. I think things are weirder in a higher dimension and very quickly. For example, in dimension 2, there is nothing non-commutative. We can always swap the legs, and dimension 3, you already have the possibility to have non-trivial non-commutative things. So yes, I don't expect I think the qubits case is very specific.
Okay, thank you. I can't see, do we have any further questions in Slack or the chat? If there are no other questions, then thank you very much, Titouan, and we're going to move on to the next paper. So paper 2, I think think we have Tejaswini. He's going to do the 2-minute presentation. Oh, sorry. And the title is The Strahler Number of a Parity Game. And you're muted. In case you're talking, you have to unmute yourself. Yes, now we can hear you.
Yeah. Can you see my slides?
Yes, please go ahead.
Yeah. So I'll be talking about my joint work with Laudavia and Marcin Wiernicki. So let me just quickly start with talking about parity games, but not in detail. I'll say that if you are given a parity game, it's known that from every vertex, one of the two players, Stephen or Audrey, wins a parity game. And recent work also shows that these winning sets have this tree-shaped witnesses of the fact that they're winning. And solving a parity game has been known to be in both NP and in co-NP for decades. But until 2017, by Kalud, Jane, Kosiniauli, and Stefan, there was no known algorithm. I mean, it was still not assumed to have only exponential time algorithms. And recently they gave a quasi-polynomial time algorithm. After this, there were several other quasi-polynomial time algorithms which fit this pattern, which is that it somehow searches for these tree-shaped witnesses in something called a universal tree. And what is a universal tree? An NH universal tree is a tree large enough that it can kind of embed any tree with at most n leaves and height h. And here you see a few examples. So highlighted in black is a tree with like 4 vertices and height 2. And here is also another tree with 4 leaves, I'm sorry. So, so we knew that this pattern was true for the following algorithms, all of which were quasi-polynomial time algorithms, which came one after the other, and they're in chronological order. And the fact that these algorithms fit this pattern was shown in this paper, which was in SODA of 2019. So, however, there was one exception, which was Lettinin's algorithm, which took this parameter k, which was called the register number, and produced an algorithm that ran in time n to the k times d to the k square. What this paper published in Lakes 2018 did was that it introduced this parameter k, showed that k was at most log n, and it also gave an algorithm whose parameterized complexity is somewhat like this. And since k is at most log n, you also have a quasi-polynomial time algorithm. And you notice this d occurring here. D is also d is the number of priorities in a parity game, and it's kind of like a fundamental parameter. So what we one of our results was to show that the register number of a parity game is equal to the Strahler number of the same parity game. And what is the Strahler number of a parity game? It was defined as the Strahler number of the tree-shaped witness in the parity game. And the Strahler number of a tree is just it's a well-known measure of its branching complexity. So what happened? Our result also helped us establish that we can find something called K-Strahler NH universal trees which are small enough. So what are these K-Strahler NH universal trees? They're just universal trees which can embed trees of small Strahler number. So more specifically, what we have is that we have obtained an algorithm that runs in time polynomial in n and in time d by k to the power k, where k is either the Strahler number or the register number equivalently. So now notice that this gives you a polynomial time algorithm if either k was constant or if you had d equals O of log n. Both of these were previously known, but we were able to extend this to a larger class of parity games which can be solved in polynomial times, and this equation holds, which is k times log d to the d by k is also O of log n.
Okay, thank you. So we have some questions. I think there were, there's one question on Slack that was already answered and one that wasn't yet answered. So why don't we start with Carolina's question? So the question is, hi, do you have any ideas about how to over-approximate the Strahler number efficiently before attempting to solve the game?
So we are, I mean, at the moment, I'm not very sure about this, but I think Marcin has master students who worked on projects where they've been trying to implement this algorithm. And I think a very crude, I don't know if I'm answering the question exactly, but a very crude idea is you can just try to restrict the number of bits used in the progress measure lifting algorithm to to reduce the search space in terms of trees, but I don't think it will do much to the Strahler number.
If maybe I can chime in.
Yes, that might be helpful.
Thank you, Tejaswini. I think a better idea is, rather than over-approximating it, is to actually compute it. And the way to compute it is to run the algorithm first for the value of k equal to 1, then 2, then 3, and so on. And this incremental process, which will not cost a lot algorithmically, just because the trees, as k increase in size. So somehow the running time will be proportional to the size of the final tree.
So you're suggesting they're actually solving the game at the same time?
That's right. So in fact, the way we are currently computing Strahler numbers of various party games is by this incremental process. And just to let you know that your hunch that you have expressed quite boldly in your papers, that the register numbers of most games are probably not larger than 2, actually seems to be quite the case. So far, among about 1,000 different very interesting party games, I think we found about 7 examples where the Strahler number is larger than 2.
Well, that's lucky for me.
3 or 4 at most.
Good to know. So I was thinking, if you just if you give all the nodes to Audrey and then try to compute a decomposition-ish kind of thing of that and find the Strahler number of that, which would be an over-approximation, is that something you can do in polynomial time, or is the decomposition going to also take quasi-polynomial time? In which case you might as well solve the game.
I mean, if you know that all the vertices are winning for Steven, then actually finding the decomposition would be in polynomial time, because you've given all the vertices to Audrey, and then now you just have a single player game. And
yeah, but you don't know whether that's winning.
But by giving all the vertices to Audrey, you might decrease the size of the dominion as well considerably, because the winning sets might change.
Yeah, and the idea is that you're decomposing something that is more complicated than your actual winning region.
It might be, but I don't know how well it would. For instance, if you had two, yeah, I don't know if would. If there is a, I don't think I can draw an image, but if
you can share your screen and there's a whiteboard.
Oh. Yeah. So if you had a Steven vertex over here, and it somehow went to a winning set over here for Steven. However, there was one small set which was not really losing, not winning for Steven, but then you end up giving this node to Audrey, denoted by a triangle. Then you'd end up losing from all vertices in W, assuming that everything ends up visiting this Steven vertex. Does it make sense? So it's just that you might end up over-approximating it to the fact that you can increase it larger than log n plus 1, which would make it losing for.
Yeah, so I was just.
I think we're almost out of time.
Oh, that's fine. I'll
Carolina,
take
I'll be
this
very
offline.
happy to continue this discussion on Slack afterwards.
Okay,
So
excellent.
Yeah,
looking forward to that.
just continue.
We can send you to a breakout room if you want. But
Thank you for the talk and the
Thank
paper.
you.
Yes, thank you all.
Yes.
Sorry for interrupting. So the next paper is paper C by Michael Benedict, Egor Kostylev, and Tony Tan. And I think Egor gave the talk, but Michael and Tony are actually here right now. So which one of you would like to go ahead and remind us of your paper?
So Peter, I will give the presentation.
Okay.
So I will share the screen.
And the paper is called Two Variable Logic with Ultimately Periodic Counting.
Yep. Well, yep. So, first, I hardly use Zoom, so so you can see the screen now.
Yes, we see it.
Okay. Okay. So this paper is about two variable logic with ultimately periodic counting, and like Peter said, the video presenter is Egor, but he cannot be here, so I'll be present and remind the thing. Now I cannot go to the next slide.
Can you do it while you're not sharing? Oh,
yeah.
So that's your desktop.
Okay. Yes. Okay.
Really.
So brief summary of our paper. I will just give a brief summary of our paper. I will have introduction, main idea, and main result. And of course, all of us, I suppose, know what first order logic is. It uses arbitrary number of variables, and but it comes to undecidable satisfiability or finite satisfiability. And if we restrict it to two variables, then the problem drops to non-deterministic exponential time, which was proved almost more than 20 years ago. And in fact, if you extend this is the so-called FO2, if you extend it with counting quantifiers, such as there is quantifiers of the form there exists 3x such that 5x whole, the complexity remains non-deterministic exponential time. Our paper is about extension of C2, which is we allow quantifiers of the form that exists as x such that phi x, which semantically means there exists the number of x such that phi x whole is an element inside S. And we call it ultimately periodic counting quantifiers because the set S, we have to restrict it to ultimately periodic sets, which we will abbreviate with UPS. And our main result is that this satisfiability for this logic is decidable, and the spectrum of this logic is also a UPS. The proof technique is reduction to regular graphs and Pressburger arithmetic. And I will just briefly explain the main idea. So the main, because it has been past 2 minutes, so I will just explain one of the main notion of the paper is actually what we call biregular graph. What is biregular graph? Biregular graph is simply a bipartite graph with vertices on the left is U and the right is V, and it has T color on the edges, which is E1 up to ET, and this set of edges are pairwise disjoint. And it is regular is because for every I from 1 to T, the degree of every vertex in U must be an element of a ultimately periodic set T. And likewise also for every I from 1 to T, the degree of every vertex in V must be an element from a ultimately periodic set T prime. And this set T and T prime are already fixed from beforehand. And this notion is actually a generalization of D-regular graph. It's a very common graph in which every vertex has degree D. And what we show in our paper is this factor of cardinalities of partitions of such graph is actually Pressburger definable, which means that they are also ultimately periodic sets. Just a simple example of this biregular
Tony, I think
graph.
we've already, all of us have already seen the talk. So, and you sort of, we only have 10 minutes. So maybe you want to just do the conclusions?
Okay, sure. This is the conclusion. Both satisfiability and finite satisfiability of this logic is decidable, and the spectrum of every sentence in this logic is ultimately periodic set. Yeah, and that's all. Yeah, sorry about the hiccup just now.
No problem, no problem. Thank you very much for the presentation and the very nice
Thank you.
talk. So now there are some questions on Slack. I'm just trying. It seems that you've already answered those.
Yeah, the moderator has decided that the question of Lorenzo Clementi has not been answered to all the degree possible.
Okay.
Yes, actually, it's the Lorenzo. It says
If you want,
here,
I can read the question. Did anybody look at first order, well, FO2 plus pair counting quantifiers of the form exist? Wow, xy to the power of s, where s is a semilinear subset of n to the 2. Right?
Yeah, indeed, it is undecidable. Eric Redel showed this already many years ago. I cannot remember that even in a form when S is just an identity, that is, I comma I, where the first component is the same as the second component, this extension is already undecidable. Basically, it's just he showed that FO2 with the extension of Harty quantifiers is undecidable. But I cannot really remember which paper is that because it was a while ago, and I will find out and put it in Slack. Yeah, thank you. Yeah.
Any live questions from the audience? I wanted to ask you, so for this logic, sorry, FO2 Pressburger, I guess, you mentioned Eulerian graphs as an example of something that can be expressed in that logic, but not in finite variable logic. Are there any other sort of interesting other examples of things that can be formalized in there that seem natural?
Well, at this point, I cannot think of any, actually. Yeah. Eulerian. I cannot think. Maybe Michael has some other idea.
Well, there are some, you can count just ask things about the domain, being even, or, it's just some unary set. I mean, this is not using the full power of the logic, but if you just look at the power of the logic for the unary set, for unary predicates, then you can come up with examples. It's tougher to come up with something that's really using the power for incidence relations.
Okay. What sort of thing about Eulerian graphs would you be able to express? I mean, it's of course obviously decidable if a graph is Eulerian or not, so that's not an interesting problem. But
say deregular graph.
Okay.
I'm not sure if it's interesting or not. Yeah.
Right.
Yeah. So every vertex has a degree d, or you can also say in a bipartite graph, the left-hand side must have degree 3, and then the right-hand side must have degree even number, or things like this. Yeah.
Right. Okay. That makes sense. All right. Are there any more questions? Because if not, then we will go straight to. So thank you very much again for the presentation.
Thank you.
I guess we're not really clapping because we're all muted, but let's imagine we do a virtual clap. So the next paper by Zachary Remskrem is on the power of a single qubit. So this is about two-way quantum finite automata and the word problem. So Zach, please go ahead.
All right, can people hear me and see my slides?
We can, yes.
Great. So in this paper, we show some new results about the class of word problems recognizable by two-way quantum finite automata. So let me just quickly remind you what quantum finite automata are, what word problems are, and what the results are. So we study the power of quantum computers that have only a constant amount of memory, which we model using finite automata. In particular, we make use of the 2QCFA. This is the two-way quantum classical finite automaton that was originally defined by Ambinus and Watrous as follows. We start with an ordinary two-way deterministic finite automaton. And then we augment this machine with a quantum register of constant size, so a constant number of qubits. And we let the machine interact with the quantum register however it likes, performing arbitrary unitary transformations and quantum measurements, and using the results of those quantum measurements to guide its computation. This is our model of a quantum computer with a constant amount of memory. Next, the word problem group. For a group G, which is finitely generated, the word problem of G consists of all strings over the generators and their inverses that represents the identity element of the group G. That is, if we have a sequence of these generators and their inverses, and we take the product, using the group operation, we obtain the identity element. That's the word problem. The key point that makes the word problem interesting is that the computational complexity of the word problem of G is extremely closely linked to certain algebraic properties of the group G. And in fact, for several natural complexity classes, there's an exact characterization of those word problems in the class. Just to give a few quick examples, it's known that the word problem of G is a regular language, if and only if G is a finite group. The word problem of G is a context-free language, if and only if G is a virtually free group. And in fact, it's even known that the word problem of G is an NP, if and only if G is a subgroup of a finite presented group with polynomial den function. So these are the kinds of results that are known about the word problem. We explore those word problems recognizable by 2QCFA. And in this paper, we show several results of the following form. If the group G has a certain algebraic property, then the word problem of G can be recognized by a 2QCFA with particular resource bounds. The thing that makes these results interesting is that in a separate companion paper, we show almost matching lower bounds. If the word problem of G is recognizable by a 2QCFA with certain resource bounds, then G has a certain algebraic property. And by combining the upper bounds from this paper and the lower bounds from the companion paper, we get the first example of a language that provably separates the class of languages recognizable by quantum finite automata in exponential time and in sub-exponential time. And that's the summary. So, questions?
To unmute myself again. Thank you, clap, clap, clap. There is a question right now on Slack, and the question is by Andrea Turini, who I think isn't in the live session, so I'm going to read the question. It says, thanks, I really like the talk, and I have a question. Have you found a relation between the complexity of a problem and the numbers of qubits in the automaton? In general, is there some inverse correlation between the quantum register size and the complexity of the solved problem?
So indeed, there are certainly results of that form within the paper, in the sense that, in addition to the few particular examples I have in this table here on the slide, there are results of the statement of the form. Well, for example, the third line of the table is, if G is virtually UK, then it can be recognized by a 2QCFA with a quantum register that has K quantum basis states, so log K qubits. And so this, at least, is a statement of the form which you asked, namely giving a larger number of qubits, a larger constant size quantum register does seem to allow additional languages to be recognized, though here I don't have a matching lower bound on the qubit number. That is, it seems like it's the case that allowing a slightly bigger quantum register gives more power, but not provable yet.
Mm-hmm. So the title of your paper is The Power of a Single Qubit, and I'm just, it's very fascinating, actually. Like, why? So I don't understand where this power comes from, because, you know, what makes quantum computers powerful is that if you have n qubits, you know, it takes exponentially much classical resources to simulate those, but it shouldn't be classically difficult to simulate a single qubit. So on the other hand, it's clearly more powerful than if you just have probabilistic computations. So do you have any sort of intuition for where that power actually resides?
Sure, it is a perfectly fair question, because the setting is rather different than the usual quantum computation setting, where we consider, as you said, say, polynomial number of qubits and our measure of interest is time. In the very small space setting, arguably every kind of quantum finite automata result exploits something which is a little bit unrealistic, in the sense that it's exploiting essentially infinite precision in the state of a qubit, which is somewhat unrealistic in the sense that real practical quantum computers are very noisy. We're nowhere near fault-tolerant quantum computers. And so in that sense, one might argue the power comes from an unrealistic thing. However, I would say there's still some value in these kinds of comparisons, going back all the way to the original Limbinas and Watrous paper from the 90s that showed in the constant size space setting, quantum computers provably outperform classical because it expresses a different way in which quantum computers can use their memory capacity. I mean, essentially, what is being used here is that even on a single qubit, one can essentially encapsulate a representation of a group in the state of a qubit. And that's where this is coming from. But as for...
I guess the point is that you're comparing finite quantum state automata to just finite state automata. So a qubit could be simulated classically, but not by a finite state automaton. It seems to be the
Indeed.
Yeah.
And that's true. A better and more succinct way of expressing what I was saying in that you're exactly right. Yeah, certainly one qubit, at least what we can say is one qubit can't be simulated by a constant number of classical bits, even given probabilistic computation.
So does anyone else have a question? Because I have one more, but I want to make sure the floor is open for questions. We don't have any questions in the chat, no. In your talk,
I have a question.
Yes, please go
There
ahead.
was a raised hand by Pratush.
Yes.
Yeah.
Hi, can you hear me?
Yes.
Yeah. So, hi Zach. Great talk, by the way. I had a question regarding what happens when you increase the number of qubits available. So, as we see, a single qubit is very powerful. So, I was wondering whether if you keep increasing the number of qubits and if there's no real limit, at what point does it become so powerful that no classical computer can do the same computation?
Well, actually, the phenomenon is a bit interesting in the sense that in the companion paper I just mentioned, and in another later paper more recently with Bill Pfefferman, we considered that sort of setting where we go to a much larger space setting, namely log space, and consider the relative power of quantum and classical computers in the log space setting. Because interestingly, a lot of the quantum advantage evaporates when one considers larger amounts of space. In particular, as shown by Watrous in the early 2000s, log space quantum computation is contained in log squared space classical. And so one has a much weaker advantage. And we have further results of that form. That is, in fact, in some sense, what happens is the opposite of, I think, what your question was asking, in that as one is giving larger and larger amounts of memory, the apparent quantum advantage disappears rather than becoming more pronounced.
Thanks.
Maybe I can quickly ask my question. So in your talk, you mentioned that CFL and DCFL are separated, but not for word problems. And I found this intriguing because it tells you somehow that word problems are more special than general problems, right? Is there some reason for that? Like,
indeed, it is a very interesting phenomenon, because as you said, DCFL is properly contained in CFL.
Right.
But there's no word problem that witnesses the separation.
Right.
And by no means is this unique to CFL and DCFL. The same phenomenon happens for several other different related classes where non-determinism provably gives no additional power in recognizing group word problems. As for why that appears to be the case, I suppose the sort of obvious answer is that there's no non-trivial certificate of membership for a word problem in any of these sort of small classes. Now, of course, it seems like that phenomenon will have to disappear eventually, as they're NP-complete word problems. And so if this phenomenon happened at the level of polytime, then NP would be equal to P.
It's fascinating.
And so,
Okay, well, thank you very much, Zach. Again, it was a nice talk. And
thank you.
yeah, so we go to paper E now, I believe. So here we have the adversarial Stackelberg value in quantitative games, not qualitative. And that's by Emmanuel Carrillo, Rafaela Gentili, and Jean-Francois Raskin, who I think is here.
Right, yes. Okay. Yeah. Okay, so I will try in 2-3 minutes to make clear what is the title of the talk. So we are considering non-zero-sum games, and so we are considering in particular what is called Stackelberg games. So they are games played by 2 players in my example here, where there is a player called the leader, another player called the follower, and they are played sequentially. So the leader will first make a choice. So he will choose a row in this matrix, and then the follower will respond by choosing a column. Okay, and so when the leader chooses 1, the follower chooses B, then the leader gets 6, and the follower gets 8. Okay, so it's a non-zero-sum game. And so the question is how to play rationally in such a game. So clearly, because the leader announces his strategy or her strategy, then the follower should play a best response to that. So it means that, for example, in our example, we have that the leader announces 1, and so here he can so the follower can obtain 8. If he chooses A, he obtains only 7, so he will choose between B or C. And so if we allow somehow the leader to make a contract with the follower and to choose between B and C, so we have a max-max problem. So where the follower will choose the maximal row, which will provide him best responses in which he can choose for the maximal value. Okay, and so this is related to some notion of Nash equilibria. But so because we want to apply those games in the scenario of reactive synthesis, so we are changing this classical definition where we change the max into a min. So this is why we call them adversarial Stackelberg games. And so now you choose the row, but then you need to face any rational behavior of the follower. So now maybe we'll choose one of its rational behavior, one of its best response, but which is not your choice, and so it's a min instead of a max. Okay, and as I said, so we do that because we are interested in reactive synthesis, and basically, so the role of the leader here is the system. So basically, you want to design a system, so you will design your system, and then the user will use it, and you would like to enforce some specification if the user or the environment is rational. And so we didn't consider in the paper the basic framework of matrix game, but we are considering infinite duration games played on graph, so very similar to the games that we saw for parity games.
Right.
But no, the winning objective is a mean payoff or a discounted sum instead of a parity objective. Okay, so the main result of the paper. So we have shown that for mean payoff games, best responses may not exist. So it makes the definition slightly more complex than what I show in the introduction. So we show also that infinite memory are useful for players to play optimally in those games. Nevertheless, we have shown that we can solve the problem in non-deterministic polynomial time, so the threshold problem. So the question, does the leader have a strategy to enforce a good outcome? And so this can be decided in NP. So we can also characterize the value, the adversarial Stackelberg value in first order logic of the reals with addition and order. And then we have shown example where the value can be approximated but not achieved. Then for the discounted sum, so we have also result that shows that the problem is difficult because we make a link with the target discounted sum problem, which is an open problem in the literature. And then because of this relation with the target discounted sum problem, we have considered approximation of the problems and shown that they are NP-hard.
Okay.
Okay.
Good. Thank you very much. Now the first question we have is from Slack, and this was asked by Liang Zhang.
Yes.
I found your presentation very nice. I would like to ask you some details. Can you provide some practical examples of the game model you mentioned in the talk? I feel that the analysis results are interesting, but I'm not sure about in what scenarios it gives advantages over other models.
Okay, so as I try to say during the wrap up, it's so we decided for that exact definition of the adversarial Stackelberg value because our motivation is in synthesis of reactive systems, where I mean this sequential characteristic of Stackelberg games is reasonable. So you first design your system, then it will be used after by so you make the hypothesis that it will be used by a user which has his own objective. And so I think that this fits very well this setting, but because you don't control the user or the environment, so that's why we changed this max into a min. And so this is the difference with what was. So for example, the max games were for mean payoff and discounted sum, they were studied before in the literature by Sven Schewe and co-authors, but this was for the cooperative Stackelberg value, not this adversarial Stackelberg value.
Okay. Are there any questions from the floor right now?
May I ask a question?
Sure.
Yes.
Yeah, so in kind of standard Stackelberg games, let's say for finite normal form Stackelberg games, mixed strategies are allowed. And in fact, it's often very useful to use mixed strategies. You get, you know, in the Stackelberg value becomes higher if you use a mixed strategy. So have you, in your setting, do you consider mixed strategies of any form, or is that not allowed in your setting?
It's not allowed. I mean, but clearly it makes sense also. So it could be interesting. But yeah, we didn't consider that because, I mean, the techniques are already quite complicated for this simpler setting. But it makes complete sense. And then, I mean, yeah, you would so for example, here when I fix my strategy, then I have the opponent that basically has a one-player game, and then he will need to optimize. So if you do consider a mixed strategy, then it will be an MDP, and so I mean problems will be more complicated, but maybe not out of reach. So this is something that could clearly be considered as a future work. Yes.
I wonder.
Oh, sorry. I was just going to do a quick follow-up. Is that in some sense, though, it doesn't quite fit your reactive synthesis story in the sense that in a sense, you're committing to something mixed, and so you're not actually building the system and letting the user use it because it's not yet, you know. Do you see what I mean? So if what you're trying to model is a reactive system where you've sort of built the system, committed to it, and then the user does something to optimize its own objective, it's not really clear what is being left randomized by the person who's committing to the strategy. Do you see what I mean? It's just a minor comment. I just was wondering how the kind of committing to mixed strategies can be justified in terms of reactive synthesis.
Yeah, I mean, for I mean, you mean for the follow-up work that could be done on this setting. So because here, what I'm saying is that assume that so the leader needs to design a protocol, and then the protocol will be used, right? And so maybe as the designer of the systems, you have some objective. But you know that your protocol will be used by some user that has his own objective. So this is the setting that we consider here. But yeah, I mean, I don't claim that using mixed strategy would make sense in that setting, but at least the questions, I'm sure that they would raise technical challenges and that are not solved by our paper. It's what was the meaning of my answer.
Okay, thank you. Thank you again. I really enjoyed your talk, and we're out of time for your paper now. So 10 more minutes we have left for the last paper in this session, which is by Mathieu Heurup. And it's about descriptive complexity on non-Polish spaces 2.
Yeah, so let me share my slides. So okay. Yeah, there. Is it okay?
Yes.
Okay, great. So thank you. So yeah, so this is the second part of a work whose goal is to develop descriptive set theory on spaces which are not very standard in a theory. So well, so descriptive set theory is about classifying subsets of topological space in terms of the difficulty to describe them. And it turns out that there are many spaces which are not captured by the theory, the classical theory, coming in particular from theoretical computer science. So when you study some sorts of computation paradigms, you end up with spaces, topological spaces, which don't have the nice properties of spaces that you meet in mathematical analysis typically. So there is a need to develop and extend descriptive set theory to these kind of spaces. So I think it was started a few years ago by Matthew Debrecht, and this is a kind of sequel to this program. Yeah, so if you have a topological space, how to measure the complexity of a subset? So there are two ways to think about that. The usual way is how is it complicated to describe A in terms of simpler sets, in terms of open sets. And there is this more recent way, which is how is it difficult to test using an algorithm whether a point belongs to the set. So these are two quite different ways of thinking, but for usual spaces, they give the same notion of complexity. So it was a nice result that we can really use the one that we prefer in nice spaces. So nice spaces are countably based spaces. Like, I mean, most of the topological spaces that you might know are like that, countably based. So what happens for spaces which are not like that? So I just focus here on one of the main results for which I have a picture, which is we study, so we start from a Polish space X, and we build the space of open subsets of X. And this is, so it's a topological space with the Scott topology. It's not Polish at all. It can be very nasty. And we try to investigate these two notions of complexity. So the topological one about describing sets, and the symbolic one about testing membership to a set. So it's called symbolic because we're actually looking at the symbolic representation of the set. When we represent points by symbolic infinite binary sequences, for instance, that's what it measures. And yeah, so what a big part of the paper is about obtaining this classification. So the bracket classes are the symbolic complexity classes, about complexity of testing the membership, and the other classes are the topological one. So in this picture, we see that there is a mismatch between the two notions of complexity. And the red ones are like the most prominent results, that there is really a gap between the two notions of complexity, which means there are sets which are easier to test than to describe, for instance. Okay, and the worst result is that there is a, sorry, I think I forgot a slide in this shorter version, but it's not very important.
And you have to leave some time for questions. So
yeah, right. So yeah, so I'm done
the talk. So maybe just
so
conclusions.
So I finish with just kind of vague explanation about why these two complexities differ, and our explanation is that symbolic complexity is more related to the sequential aspects of the space, and topological complexity is related to the aspects of the space in terms of open sets. And yeah, I'm done. Thank you.
Okay, thank you. Now there is a question that has been asked on Slack during the session. It's by Elke Neumann, and the question is: now we have two descriptive set theories on QCV0 spaces, a topological one and a representation-based one. Results by Debrecht and Pauli indicate that the representation-based approach is quite promising. For example, you have analogs of the Jane-Rogers theorem or the Hausdorff-Kuratowski theorem. How much is known for the topological approach, besides that it can differ wildly from the representation-based one? Do your results, for example, the failure of the topological version of Wedge's lemma, somehow indicate that the topological approach is misguided?
Yeah, so right, indeed, it's these results strongly suggest that the topological approach does not work very well. So I think we need more results to have a definite answer. But yeah, it makes sense because incountably, I mean, the descriptive set theory was already developed in countably based spaces where open sets are easy to describe and you have this countable basis. So it's normal, it's justified to look at countable unions, countable intersections. But in a space which has no countable basis, it's not clear that the usual notion of topological complexity really makes sense, because even the open sets, the simplest sets, are difficult to describe. So how is it justified to define the Borel hierarchy or things like that? So yeah, so indeed, the Elke Neumann is right about the fact that topological complexity may not be the right notion.
Okay. Are there any questions from the floor? I was wondering, so in your talk, you mentioned there were sort of two classes of results, because first you investigated polynomials as a space, and then the O of X.
Yes.
The open sets, I guess, on it, where X is sometimes Polish. And in the polynomial case, the agreement between the two versions was at delta 2 and above.
Yes,
but
right.
In the O of X case, it was below d omega. And then there was some
right. Yes. Yeah.
So why is it that, I mean, is there any rhyme or reason to this, or what makes?
Okay, so for the polynomials, for instance, the point is that we have some discrete parameter, which is the degree on the polynomial. And in a sense, this parameter is difficult to find, but you can compute it in the limit. If you have just the coefficient, you can find the degree in the limit, so in a delta 2 way. So that's why from delta 2, you have the degree for free in a sense. And so everything behaves well after level delta 2.
I see.
But for open subset of a space, it's not a discrete parameter. We need an infinite continuous parameter, and this makes things very bad.
Okay. Thank you. Are there any other questions from the floor? If not, I suggest that at this point, all of us can unmute ourselves and clap so that we have applause for all of the speakers in this session. They all did a wonderful job. So it was a very nice session, and I think anyone who's interested in continuing discussion with the others could just stay for a while, even though the session is officially ended. And also there's the Slack channel, which I think will remain open for a while. People can ask follow-up questions. And is there a social meeting or anything now, or?
There is just a break, but you can use this link, I think, except that I think Maximilian has to move on, but this will work. I mean, our technical person.
I will need my Zoom license for the next session.
Yeah.
I see.
Yeah, so we have another few minutes if you desire so.
I mean, anyway, follow-up discussions can be held in Slack as well. So, and the break is just an unstructured break?
It is just an unstructured break, yeah.
Bring your own.
Yeah. Yeah, what we do is now let's say the plenaries will be extended. The Q&As are too distributed, I think, to organize. But of course, you can chat if you so desire.
And we start in half an hour. Is that true?
25 minutes.